So I've been a clinical geneticist for 40 years, and we've for a long time hoped that the day would come when we could get a DNA result, in the clinic. And I think we're now actually reaching the point where that becomes a feasible proposition. First of all, we've got the discovery process, and that's going to mean a lot of patients having whole genome sequencing, and this conference that we're at is discussing all of the challenges of that. But what we've got to remember is that very often that will distill down to a specific cause for a specific condition. And when you've got a single point mutation to deal with, then it becomes entirely feasible to do a same-day diagnosis. I think in the whole world of DNA testing, we need to draw an analogy with computing. Back 30, 40 years ago, people said we'd only need 4 or 5 computers for the whole planet. And then we realize now computers are everywhere. We do have huge supercomputers, and we carry them in our pocket and on our wrist. And I think the same thing will happen with DNA testing. Some of it will inevitably involve whole genome sequencing, complex annotation and analysis. Other things will be very simple, particularly pharmacogenetics. I'm about to take warfarin. There are 3 variants in the P450 and VQRC1 gene that tell me whether I'm sensitive or not. I don't need my whole genome sequencing to do that. And that's the sort of test we can reduce to a few minutes. The receptionist could do it while you're waiting in the waiting room. What you do with that result, first of all, you need to be sure that it's reliable, and that's what the process we're currently in. But then there's the usual process of handling it in the clinical setting. But the good thing is, it's all contained within one visit. So it's particularly relevant for those situations such as a prescription of a drug or infectious diseases. We can use the DNA sequence of the infectious agent to make a diagnosis on the spot. I think we're in a sort of a bit of a race, and there are 2 competing concepts here. One of them is develop high throughput industrial style whole genome sequencing, get that into the medical record either when you're admitted to hospital or when you're 18 or when you're born, and then you biopsy the data to ask specific questions of it in different settings. And the other, and not necessarily competing but contrasting approach, is to say let's do whole genome sequencing in the research setting, identify the key changes that will be actionable. For example, a particular point mutation that tells me this drug will work in this tumor, and push that as close to the front as you can, because it takes a lot of the sample transfer and cost out of the system. It's great in an American setting in terms of billing. It's great in Africa because you can't ship samples. So wherever you can push it down to the ground, we will. One of the obvious attractive areas for DNA technology is infectious diseases, and especially being able to diagnose on the spot in a sick infant, for example, whether a particular pathogen is present. And we've been working with Yale on some novel technology using electrical fields to actually isolate cells of particular types. So that creates enough signal to then do a DNA extraction and a PCR on the spot. And that's looking very promising. So I think we can envisage the time where if you've got a child with septicemia, or you've got someone feverish at an airport in a zone where there is an epidemic running, you could actually isolate and test an infectious agent on the spot. And that would obviously be hugely powerful, especially also with, say, an itinerant population with tuberculosis, where you can't ask them to come to the hospital. They're living under a bridge. You need to test them right there and then.